Okay, so this is part 2 of the examples, and so what we've already done is the first worked example, which I did with you, and here you can see a typed up version of that. So what we're going to do is move over to the examples that you were doing, and so the first thing you needed to do was to complete the table of values for each of the functions, and here what you can see is examples of where I've shown the substitutions for f of minus 3, for instance. And so if we go to the f of x, these are the values that you should have obtained for the f of x function. Of course, the f of x function is 2 to the power of x. So if you subbed in minus 3, as you can see from above, that calculation is shown, and our y value should have been 1/8. I haven't shown all of them, but as you can see here, we've got x is minus 2, y is a quarter, x is minus 1, y is a half, and so forth. And as you can tell from each of these, as you go from value to value, we are multiplying by 2. So our growth factor, if you will, is an increase of 2 each time. Okay, and so using the same approach, if we look at the g of x function, and the h of x function, which I'll highlight in yellow. H of x, as you can see from the bottom, we had our f of x function. Our g of x function was 2 to the power of x minus 3. And so I think I've just made a small typo here, so this should in fact be the g of x function. Apologies, that's g and this is h. But what we can see from the values here is that for each of these functions we can in fact use the original values. And so if you were to look carefully at each of the functions, here is 2 to the power of x. The g of x function is 2 to the power of x but minus 3. And so if we go back up to the table, in each case the g of x function should be 3 less than the corresponding f of x value, because it's the same function, just subtract 3. And similarly, if we go and we look at the h of x, the h of x function is simply the negative of the f of x function. And so if we come back over here, you'll see once again we have got the f of x value is exactly the same as h of x, except it is a negative in each of the cases. And really what we want to do at this point is have a look at what the implication of that is for the graph. Okay, so if we come down over here, we have our original f of x graph, 2 to the power of x, and there's certain key points, of course. We could read those off the graph. When x is 2, y is 4. When x is 0, y will be 1, and so forth. What happens, as you can see with the g of x function, is that the shape is identical, but if we were to pick any point and go down from the f of x graph to the g of x, the distance between those is 3 units along the y-axis. Likewise over here, it doesn't really matter where we pick on the graph, even up to the right. The difference between those two in terms of the y-coordinates is of course 3 units, because the g of x function is just below. So identical shape, just 3 units down. And hopefully what you realized as well was that if we had the range for the f of x function, which gets closer and closer and closer to the x-axis, y greater than 0, then your range for the g of x function, which was 3 less, should have been y greater than minus 3. And so as you can see here, the graph gets infinitely close to the y value of minus 3, but never reaches that. And then our final example was the function of h of x, which was minus 2 to the power of x. And so what that does is it multiplies the entire f of x function by a negative. What you can see graphically is that any y value that was a positive becomes a negative, and the graph basically gets flipped upside down. And this function is in fact not a growth function, but a decay function. As the value of x increases, the value of y gets smaller and smaller. And so in that case, it's a reflection of the growth function. And in this instance, we do have y values which are negative, but that is because the graph has been flipped upside down. And that again we'll talk a little more about in a future lesson. And so the final part, if you've managed to get these answers correct, you'll find this note posted on your Google Drive, and you can check your answers, detailed answers there. The last thing really that I just wanted to mention was some of the uses to which we can put exponential functions. As mentioned in the introduction lessons, what we use functions for are mathematical models, and exponential functions are particularly useful for modeling several phenomena. This includes population growth. These typically follow exponential growth models. The spread of disease is typically an example of something which can be modeled very effectively using exponential functions, as can financial growth and decay. And this is just an example of human population to date, and as you can see from the shape of the graph, it follows with some exceptions because of naturally occurring disasters or events, but it basically follows very closely to the exponential growth model, and so that therein lies the massive use of the exponential function, which we'll talk more about in coming classes.